you can trust the results calculated in QuickField. Now let's move to the next case. This is the real transmission line. There are 3 phase conductors. There is the ground surface, and there is the transposition of the conductors. And again, our task is to calculate the inductance. Of course, there are several inductances here. The magnetic flux linked with the phase A depends on the current in the phase A and the current in the phase B and in the phase C. So there are self-inductance and mutual inductance between conductors. To get the best result, you should repeat the experiment. So in this problem, we will try to repeat the experiments that you will do with a real transmission line. And in a real transmission line, you do not measure fluxes, you measure the voltages and the currents. So this is QuickField, and the problem type is AC magnetics. The transmission line carries the AC current, and to simulate AC magnetic field, I choose the problem type AC magnetics, and the frequency of the current is 50 Hz. The length of the transmission line is 120 kilometers. Let's take a look at the geometry model. There is the air block, and for the air block I specify the magnetic permeability of 1. And there are 3 phase conductors. A, B, and C. C conductor, A, B. A on the top, B on the right, C on the left. For each conductor, I specify the magnetic permeability of the material and the electric conductivity. Also, there is the ground surface with 0 potential, and the calculation area is surrounded by the boundary. And once more, in this problem we have the electric circuit. There are no field source specified in the label properties. The sources are specified in electric circuit. So this is the electric circuit. These are voltage sources for the phase A. I specify the magnitude of the source and the phase. For the phase B, I have the phase 120, and for the phase C, I have the phase of 240. These are the conductors, and this is the load. So my transmission line, this is my transmission line, is connected to the three-phase source, and the other end of the line is connected to the three-phase load. The simulations run simultaneously. Both the field part is simulated and the circuit part is simulated. Let's take a look at the simulation result. This is the field distribution, the magnetic field distribution produced by my transmission line. Again, I would like to repeat the real experiment. I will not measure the fluxes, I will measure the currents and voltages. These are the circuit simulation results. Now you know that the transmission line conductors are not symmetrically placed above the earth. So each conductor carries slightly different current because each conductor features slightly different inductance. What is done in practice? In practice, you have the transposition. After some distance, the conductors change place so that overall inductance of each conductor is the same. Let's simulate the transposition in QuickField. This is my simulation case of the transmission line without transposition. The transmission line total length is 120 kilometers. And now this is the new problem. Let me show you the geometry model. The geometry model consists of 3 parts. Each part represents its own condition, its own position of the phase conductor. So here we have A on the top, B on the right, C on the left. And here we have C on the top, A on the right, B on the left. And here we have C on the right, A on the left, and B on the top. So this model consists of 3 independent models, and these 3 models are connected through electric circuit. This is the electric circuit. In fact, this phase conductor consists of 3 parts. 1, 2, 3. And B conductor consists of 3 parts, and the C conductor consists of 3 parts. So this is the 3 by 40 kilometers parts in my model. And I changed the model length to 40 kilometers. Now let's take a look at the result. These are 3 parts of my transmission line. Part 1, part 2, part 3. And let's take a look at the circuit result. Now, each conductor carries the same current. So, applying the transposition, we distinguish the disbalance in currents. And this can be simulated with QuickField. Now to the next case.